3C, measures of position. So we spoke about measures of center, where's the middle of the data, and measures of variation, how much does it change or how much does it spread. Now we're going to talk about measures of position, so locating data points within our data. And the first thing we're going to talk about with that is a Z-score or a standard score. The Z-score is found by taking the data value and subtracting the mean and then dividing by the standard deviation. What this does is it basically turns the difference between the data value and the mean into a measure of standard deviations. How many standard deviations away from the mean is this data value? Now, that may sound familiar. How many standard deviations within this many standard deviations? The percentage of data with it, right? When we were talking about the empirical rule and Chevyshev's inequality, we were dealing with standard deviations away from the mean. So the Z-score takes any data value, compares it to the mean, and then by dividing by the standard deviation, says it's this many standard deviations away from the mean, which allows us to compare apples and oranges. Okay, it allows us to compare two completely different things. I'm 5'11", so I'm going to put x sub d as 5'11". So that's 71 inches. Now, this is a point where if I was in an actual classroom setting, I'd pick on someone that I was guessing was somewhere around 5'4" or 5'5". And we'll say I pick on and a female who is 5'4" or 5'5", just to make it fit. So we'll call this female Sue. So Sue is 5'5" or 65 inches tall. Now I'm 71 inches tall. Sue is 65 inches tall. Therefore, I am a good 6 inches taller than her, which basically means I can stand behind her, look right over her head. Now, because of that, I could say, you know, Sue, you're a midget, you're kind of short. You know, I could say that from my perspective. Now, first of all, that wouldn't be a very nice thing to say. Secondly, you may look at that and go, but Mr. Davis, that's not really fair for you to call her short. You're a male, she's a female. Aren't females inherently shorter than males? And that's an excellent point. If I were to look at the average height of males, the average height of males is 5'9"3/4". So about 5'10". So I can see the average male is 70 inches tall. And the standard deviation for heights of males is approximately 3.1 inches. Whereas for females, the average female is 5'3" 3/4", or approximately 5'4". So 64 inches. So the average female is 64 inches tall with a standard deviation of about 2.8. I am not making these numbers up. I made up Sue's height and that's it. Okay? But these numbers are accurate. So if we're looking at this, is it fair for me to say that Sue is short because I'm 6 inches taller than her? Well, if we look at the average heights, males tend to be 6 inches taller than females on average. So maybe in comparison to one another, we're really the same height. Or at least in comparison to our genders, we're essentially the same height. But then we have our standard deviations to bring into place. So what we're going to do is we're going to find my Z-score and Sue's Z-score and see in comparison to our others of our gender, who's taller. So I'm going to do Z sub D, that's me. So you get X is 71 minus 70 over sigma. Oops, don't write it as sigma, write it as 3.1. Okay, so we got 71 minus 70, or that's 1 over 3.1. 1 over 3.1 Just grabbing my calculator. Gives me 0.32. So I am 0.32 standard deviations taller than the average male. And now if I find the Z-score for Sue, she is 65 inches tall, minus 64, the average height of a female, over 2.8, which gives us 1 over 2.8. So 1 divided by 2.8 gives me 0.36. So Sue is 0.36 standard deviations taller than the average female. So even though I'm 6 inches taller than her, and even though the average height of males and the average height of females differ by that same 6 inches, due to the standard deviations, the fact that female heights have a smaller spread than male heights, in comparison to our genders, Sue's actually a little taller than me. So much for picking on Sue for her height. If anything, she can pick on me, saying that, compared to her, I'm a little on the short side. So my wife, who's 5'6", 66 inches, as you can see, even though I can pick on her because I'm 5 inches taller than her, in reality, in comparison to our genders, she's quite a bit taller than I am. So that's Z-scores. And you can see how that would actually fit in with our empirical rule and Chevy inequality. In fact, if we look at someone who is, if we look at a mean of 100 and a standard deviation of 15, and you have a data value of 115, then we should see that the Z-score is equal to 115 minus 100 over 15 is equal to 1. So if the data value is exactly 1 standard deviation away from the mean, then your Z-score is going to be exactly 1. If it's 2 standard deviations away, your Z-score is going to be 2. So we can see the relation between these Z-scores. And a little later on in the course, we're going to get introduced to the normal distribution table, or the cumulative probability of normal distribution table, and we'll see where these Z-scores come into play. Okay, so what about other measures of position? Well, let's look at percentage or percentiles. When you're talking about percentiles, percent per 100, you're breaking your data up into 100 different pieces. And so if we have a listing of data values, we can find what percentile each data value is in, or we can find out what data value is in a certain percentile. So let's get some data up here. Let's say we've got 27, 38, 19, 24, 29, 32, 21, 17. So I have 1, 2, 3, 4, 5, 6, 7, 8 data values. So I'm going to put that down. N is equal to 8. And I want to find percentiles, or I want to find out what percentile a certain data value is in, or what data value is in a certain percentile. So if I want to find out what data value is in a certain percentile, then I'm going to use the following formula. L, which is just going to give us a position in my numbers, is equal to percent divided by 100 times n, our sample size. So that's going to tell us the position that a particular percentile is in. Now, there's a couple things we need to do with this. One, we need to realize that if L is a whole number, then we're going to average the values in position L and L plus 1. So find L and L plus 1 and average. Let me spell that word. Actually, it looks like the word average. And if L is not a whole number, then we're going to round up, which does not start with an F. And that's going to give us the position of that percentile. The other thing I want to point out is that we need these numbers in numerical order. Remember when we dealt with the median, we were finding the middle data value? We need the numbers in numerical order. You can't just take them as they are. So let me switch to a different thing. I'm going to put my calculator over here. So let's put these in numerical order. So 17, 19. Let's see. It was like 21, 24, 27, 29. 32, 38. And just as we did when we were dealing with median, let's just make sure we still have all our data values. 1, 2, 3, 4, 5, 6, 7, 8. I know it seems ridiculous, but to be honest, so many mistakes come from people just losing a data value when they're reordering their numbers. So just take that few moments to say, okay, n is still equal to 8, I still have all my data values. It will make your life much easier. So I've got that. So now, let's use this to find, so let's say I want to find out what number is in the 42nd percentile. What value is in the 42nd percentile? So there's my question. What value is in the 42nd percentile? Well, I'm going to plug into this formula. 42nd percentile, so 42 over 100 times 8. And that's where I grab my calculator again. 42 divided by 100 is 0.42. Times 8 gives me 3.36. If L is a whole number, find L and L plus 1 and average. Okay, not a whole number. L is not a whole number, round up. So we're going to take that 3.36 and make it 4. So that means the fourth number in this reordered set of numbers is going to be the 42nd percentile. So it'll be 1, 2, 3, 4. So 24 is in the 42nd percentile. And that's how we do it. So if we have a certain percentile, we want to find out what number's in that percentile, put the numbers in numerical order, take that percentile and divide by 100, multiply by n, the number of data values, and if it's a whole number, take that position in the next one, and then average those. If it's not a whole number, round up to a whole number, and that's round up. Don't just round up to a whole number. So 3.36 became 4, and go to that position, and we now have the number in that percentile. Well, we can go the other way too, and say, well, what percentile is a certain number? So if I want to know what percentile a certain number is, first of all, this time I'm going to put my data in order up here. 17, 19, 21, 24, 27, 29, 32, 38. And remember, we checked to make sure that was all 8 of them. Okay, so now if I want to find the percentile of a certain number, like let's say I want to find the percentile of 32. I'm going to use the following. P is equal to, and I apologize, there's really not a better way for me to write this, the number of values to the left plus 0.5 divided by n times 100. Okay? So the number of data values to the left plus 0.5, all of that divided by n multiplied by 100. So what does that mean? Well, I'm looking for 32. That means I count the number of data values to the left of it. So 1, 2, 3, 4, 5, 6. There are 6 data values to the left of it, plus 0.5, divided by n is 8, times 100. So I have 6.5 divided by 8, times 100, or 650 divided by 8, which is 81.25. So 81.25. So put a percent on that. And the number 32 is in the 81.25 percentile. And to be honest, I'm not that picky. If you want to call that 81%, have at it. I'm okay with rounding that to a whole percent. And I'll tell you why I'm okay with that. The biggest reason I am okay with that is because in reality, we only have 8 data values here, which means each of these data values covers a range of about 12.5%. This says 81.5 for 32. If I said what data value is in the 77th percentile, so 77th percentile, and I want to do that, let's use our previous method. That's L is equal to 77 divided by 100 times n is equal to 0.77. Oh, what was n? N was 8 times 8. So 0.77 times 8 gives us 6.16. 6.16, which when we round up gives us 7. 1, 2, 3, 4, 5, 6, 7. Look at that. 32 is in the 77th percentile. But we just said that it was in the 81st percentile. Well, what if I go the other way and I take it to 86%? L equal to 86 over 100 times 8. So 0.86 times 8 gives me 6.88, which rounds up to 7. And again, I'm at 32. So 32 is in the 86th percentile. The problem is we have such a small amount of numbers that when we start breaking it into 100 parts, each one of these accounts for numerous parts of that. If we had over 100 data values, then you wouldn't run into this problem. Because then you could break it into 100 equal parts, and each one of these would have its own percentile, or depending how large our data set was, even one percentile may cover a number of data values. So That's dealing with percentiles. We either start with a percentile and determine what number is in that percentile, or we can start with a data value and say, hey, what percentile is it in? So that's dealing with percentiles. Now what I want to do is I want to go into quartiles. Now percentiles, I know you've heard of those before, whereas quartiles you may not be as familiar with, and that's okay. Get rid of that calculator for a moment. Switch back to my black marker. So, what are quartiles? Okay, so quartiles are just like percentiles, except for now we're breaking our data into quartiles, or 4 parts. Okay, and I'm going to draw a visual here. This is not how you do quartiles. I just want us to be able to see what's happening here. So let's say I have a rectangle, and I want to break this rectangle into 4 equal parts by splitting it with vertical lines. Well, how many vertical lines do I need to come up with to do that? Well, I can use one to split it in half, and then I can use another one to split that half in half, and another one to split this half in half, and we see that there are 3 dividing lines that I need to come up with, in addition to the starting line and the ending line. We can relate these to the quartiles, that the starting point is q sub 0. That's a 0. We use 0 a lot of times for the initial value of something, the starting value of something. So the 0th quartile, the 1st quartile, the 2nd quartile, the 3rd quartile, and the 4th quartile, which is equivalent to the 0th percentile, the 25th percentile, the 50th percentile, the 75th percentile, and the 100th percentile. So we could use those methods that I just talked about for finding percentiles to find the quartiles. We're not going to though, because that seems like work. And there's a much simpler way to find quartiles than to find all the percentiles. That took some calculation, finding positioning, determine all that stuff. We don't need to do that. But this is a good visual of what we're going to be doing. We're going to use 5 points, which when you're dealing with quartiles, it's sometimes referred to as the 5-number summary, or the 5-point summary. Because we're going to use 5 points to describe our data. So let's start with a set of data here. 86, 71, 92, 98, 59, 78, 83, 87, 91. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's give a few more data points here. So 91, 69, and 24. Okay, so let's assume these are test grades. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 test grades. And I want to find the quartiles associated with these test grades. Well, the first thing I'm going to do, of course, is put them in numerical order, just like I did for percentiles. So we're going to start with 24, and then the next one's 59, and then 69, 71, looks like 78, let's see, 83, 86, 87, and then what do we have? 91, 92, 98, And what do we do at this point? We make sure that we included all of them, right? We expect 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we have them all there. If I missed one, my count would have been off, and then I can go back and fix it. So this is how easy it can be to find quartiles. Well, the first data value is always the first quartile. Sorry, the 0th quartile, right? It's always the first one that occurs, Q sub 0. So the 0th quartile, that's also the minimum value. The last data value is always Q4. That's the maximum value. Then, remember when I did my box, I split it in half first, because it's easy to split something in half, right? So I can find the middle value. It's really the median, isn't it? So I just have, if I've got 11 data values, 1, 2, 3, 4, 5, 6. So there's Q2. That's the median. So I found the minimum, the maximum, and the median of my data. And then to find Q1 and Q3, what I'm going to do is I'm going to use this median to split the data into two halves. Remember how I did it when I had that rectangle? I split it in half, and then I split each half in half. So now that I've split this in half, 78 and down is part of the first half, 86 and above is part of the second half. I'm just going to find the median of those halves. So I got 1, 2, 3, 4, 5 data points. So the middle one's going to be 69. So that's Q1. And then I've got 5 over here. The middle one's going to be 91. That's Q3. So my quartiles are 24, 69, 83, 91, and 98. That's not bad. Heck of a lot faster than finding the percentiles and working it through it that way. And that gives us our quartiles. So find the minimum value, that's Q0. Find the maximum value, that's Q4. Find the median, that's Q2. Use that median to split the data in half. And then take the median of the first half, that's Q1. Take the median of the second half, that's Q3. Now, if we have an odd number of data values, that works beautifully because the median is going to be the middle number. What happens if we have an even number of data values? Well, to do that, I'm just going to do a quick, simple example. And when I mean simple, I mean I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Quick, easy numbers in order. So what happens? Well, I go to the first one, and I go, there's Q0. I go to the last one, there's Q4. 10 data values, so I'm going to take the middle two, 5 and 6, that gives me 5.5. There's Q2. Now here's where it changes a little bit. Notice that Q2 is between 5 and 6. So therefore, 5 is part of the lower half. 6 is part of the upper half. Notice here that 83 was my dividing line. It was not part of either half. Here, that 5.5 is in between that 5 and the 6. So 5 stays with the bottom half, 6 stays with the upper half. Now I have 5 data values. So that's going to be Q2. I have 5 data values. That's going to be, Q1, wrote my number, and that's going to be Q3. So I have Q0, Q1, Q2, Q3, Q4. So that's the only real trick you have to watch out for is if you have an even number of data values, it's going to split it in half. You're going to find your median by taking those middle two, and the two parts that are used for that are going to stay with their respective halves. So that's finding quartiles. Well, that's great. Well, let's go a little beyond that. Say, okay, so I found the quartiles. Well, what does that tell me? Well, it tells me a number of things. First of all, remember how we talked about outliers? And we said that it's kind of a subjective thing. Well, that seems to be pretty far away from the rest of the data. Well, with quartiles, we can now determine whether we actually have outliers, and we can do it numerically. So we have a mathematical reasoning behind it as opposed to just saying, gee, that seems far away from the other data. I look at this and I go, gee, that 24 seems far away from the rest of the data. So I'm guessing it's an outlier. But how am I going to prove that? Well, we're going to start out by finding the interquartile range. Or IQR. The IQR is found by taking Q3 minus Q1. So basically, remember, Q3 is the 75th percentile, Q1 is the 25th percentile. We're essentially taking the middle 50% of the data and saying, what's the range of that? So in this case, that's 91 minus 69, which gives us 22. So that's the interquartile range, 22. Now, what we're going to do next is we're going to find our expected minimum value and our expected maximum value. We call those the normal min and the normal max. So I'm going to use lowercase n, lowercase m for normal minimum. Basically, where would we expect the data to end on the low end? And we're going to use lowercase n, capital M for normal maximum. Where would we expect the data to end on the high end? Based upon this interquartile range. So my normal minimum is found by taking Q1 minus 1.5 times the IQR. 1.5 is a constant. It is always used as such. So that number does not change or vary in any way. It does not come from our data. It's always Q1, the first quartile, minus 1.5 times the interquartile range. So in this case, Q1 is 69, minus 1.5 times the IQR is 22. Order of operations says multiply before you subtract. Don't fall into the trap of going 69 minus 1.5, well, that gives me 67.5, and then multiplying by 22, you're going to come out with some ridiculous number. So 1.5 times 22 is 33. So we have 69 minus 33, which gives us 36. So 36 is our normal minimum, meaning we would expect with this interquartile range that our lowest data value would be 36. So any number less than that we consider to be an outlier. We come here, we go, aha! 24 is less than 36. 24 is an outlier. Well, what about our normal maximum? Well, that's Q3, 91 plus, let's put the equation here first. Q3 plus 1.5 IQR, which is 91 plus, and I'm going to save some time, that 1.5 times 22 was 33. 33 gives us 124. So we would expect our maximum value to be 124. Any number greater than that we would call an outlier. Well, we came out with 98 as our highest value. It's not greater than 124, so we do not have any outliers on that side. But we can say that 24 is an outlier. I think that actually looked like a 4. There we go. So 24 is an outlier. So what did we do to find the interquartile range? We took Q3 minus Q1. We found the range of the inner 50% of data. And then we used normal min, normal max. We said Q1 minus 1.5 times IQR and Q3 plus 1.5 IQR to determine where we expected our minimum value and our maximum value to be. And then we looked and said, are there any data values outside of the range? Anything less than 36, anything greater than 124. 24 was less than 36, so we said, yep, we've got an outlier. So now we've proven mathematically that 24 is an outlier. whereas before we had to just say subjectively, it seems like it's an outlier. Okay, final thing we can do with this. I'm going to leave that data there. I'm going to work with that. But now we're going to deal with box plot or box and whisker plot. So, box plot, I'm going to say also a box and whisker. So a box plot or a box and whisker plot. Basically, it's a way to represent this 5-number summary, these quartiles. And it's very simple to do. A box plot is done by giving yourself a number line. So you take that number line, and you want to make sure it covers your data. So we want to go from 24 to 98. So I'm just going to 20, 30, 40, 50, 60, 70, 80, 90, 100, okay? And then we're just going to mark our quartiles with vertical lines. 24, give it a vertical line. 69, vertical line. 83, vertical line. 91, vertical line. 98, vertical line. So that's all we did. We just put 5 vertical lines on there, marked our 5-number summary. Now, we're going to take the middle 3 lines and just tie the top and bottom together to give us a box. Box plot, right? A box. And then we're going to go from the right-hand side of that box out to our maximum. And from the left-hand side of the box out to our minimum. And thus we have a box plot, otherwise known as a box and whisker plot. That's how simple it is. Once you have your quartiles, put them on a number line. Please, 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 number your number line first to cover all your data, then put the lines in place. Do not go 24, 69, 83, 91, 98, evenly spaced, and put your box plot, because it's going to look the same every single time. It's going to be wrong. Create your number line, then put your vertical lines for each of your quartiles. Tie the middle 3 together with a line at the top and bottom, create your box, and then create your whiskers out to the min and max values. So that is a box plot. And they're kind of cool because I can look at this and I go, whoa, look, I got like the inner 50% of the data is here, and then it seems to trail off to the left-hand side. Gee, that kind of looks like this is left skewed, right? The bulk of the data is here, and it trails off to the left-hand side. I may have a left square distribution, or left skewed distribution, and I can kind of see that from my box plot. Now, there is a modification to a box plot. It's called a modified box plot. I'm going to get rid of the box and whisker plot part of it. And I'm just going to call this a modified box plot. The difference between a box plot and a modified box plot is that the modified box plot takes into account outliers. So everything works the same, except what we're going to do first, before we do anything else, is we're going to mark any outliers. And we tend to use like an asterisk for it. So that's showing that we're going to have an outlier. That looks kind of ugly on the monitor, so let me make that look just a little bit better. There we go. Okay, so there's our outlier, and then what we're going to do is, once we've plotted our outliers with these asterisks, and if there's more than one outlier, we plot them all, then we go past the outliers to the next data value that's not an outlier. We treat that as that's the minimum or the maximum value, depending which direction we're coming from. So we're going to look at 59 and say 59 is going to get treated as our minimum value. Nothing else changed, so our Q1, our Q2, our Q3, and Q4 all stayed the same. And now we see that we have our outlier and a distribution that now looks a lot more symmetric. We know it's not perfectly symmetric because you've got 25% of the data in here and 25 in there in a much larger gap, so it's obviously not perfectly symmetric, but it looks much more symmetric than it did before. So the only time you give a modified box plot is when you're asked specifically for a modified box plot, and the only difference between a box plot and a modified box plot is that a modified box plot, you indicate any outliers first, then you go in past the outliers and use those for your Q0 and Q4 to create the rest of your box plot. So there we go. And if you have no outliers, then a modified box plot looks exactly like a standard box plot. That's measures of position.